A very warm welcome to today's IMechE webinar organized by the Thermofluids Group. Our speaker today is Simone Mancin, who is an associate professor at the Department of Management and Engineering of the University of Padova, where he teaches applied physics, thermofluid dynamics, and thermal management of electronic devices. Simone founded the Nano Heat Transfer Lab, which is mainly focused on experimental and numerical analysis of single and two-phase heat transfer inside porous media, microgeometries, and nanostructured materials. His research aims at developing innovative solutions for smart, efficient, and compact heat exchangers for refrigerations, air conditioning, and electronics cooling. He is the co-author of more than 150 papers in international journals and proceedings of international conferences. He is the associate editor of the Heat Exchanger Design Handbook, the Journal of Mechanical Engineering Science, and he is also a member of the editorial board of International Journal of Thermofluids. Simone graduated with distinction in mechanical engineering at the University of Padova, where he also gained his PhD in industrial engineering, applied physics. Over to you, Simone.
Hello, everyone. Thank you for joining this webinar. I would thank Francesco for his introduction. And today I'm going to talk about the enabling technologies for efficient latent thermal energy storage. I'm Simone Mancin from University of Padova, and I'm where I lead the group on nano heat transfer. And today, I'm going to show our perspective related to this topic. So how can we imagine to enable the latent thermal energy storage technology and for a future applications? First of all, I want to introduce the Nano Heat Transfer Research Group at the UniPD. Then I will discuss briefly why there is a difference, a strong difference, and which is the strong difference between the engineering and the scientific point of view, even if I'm an engineer. Then I will discuss a little bit about the PCM we are studying and which one are going to be interested in the future. I will compare the porous media versus the 3D periodic structures, okay, and which is the new research path we are working on, and suggest to be important and to be followed in the next future to achieve the deployment of such technologies for a sustainable future. As you can see here, the research group consists of two full professors, so Giovanni and Claudio. Then there is another associate professor, a part of me, who is Luca. And then we have an assistant professor, brilliant Giulia Righetti. And then we have a visiting professor from UQ, Australia, University of Queensland, and Professor Kamel Houman. Hi, I'm a mechanical engineer. I'm associate professor at the Department of Management Engineering, and as I told you, I work mainly on the Nano Heat Transfer Lab. I'm leading the research group. We have 4 PhD students. 2 of those work at the University of Padua at Nano Heat Transfer Lab, but they are co-supervised by the UQ Professor Kamel Houman, and 2 other PhD students are co-supervised by me, and they work mainly at the University of Queensland. Their research is devoted on renewable energy and the application of latent thermal energy storage for concentrated solar power plants. Other 2 PhD students will join the group next fall, so the group is growing very fast. So the research activities are conducted in 2 laboratories, the Refrigeration and Air Conditioning Lab and the Nano Heat Transfer Lab. The first is mainly focused on the industrial application, while the second one mainly mainly focused on pre-competitive studies, also funded by the industrial partners, and the idea is to investigate the possibility to deploy and implement micro and nanotechnologies in the current and the future heat transfer applications. The research group will organize a PCM 2021, so it is focused basically on this topic. Okay, and PCM 2021 is the 13th IIR conference on phase change materials and slurries for refrigeration and air conditioning. It will be hosted in September, hopefully, if this pandemic issue will go away. If you want more information, you can just go in the website that you can see in this slide. The Nano Transfer Lab was initially called Nanofluids Lab in 2006. And then when I joined the research group, we renamed the lab as Nano Transfer Lab to open more application for nanotechnology. So now at Nano Transfer Lab, we look at the nanotechnology as a whole, trying to introduce nano and also, of course, microtechnologies in the advanced heat transfer solutions. And here you see a list of the main research activities, which are related on PCM and latent thermal energy storage, on nano PCM, nano emulsion, water plus paraffin, for instance, nanofluid boiling for surface functionalization, micro and nanostructure surfaces for flow boiling and pool boiling heat transfer enhancement, and again something related to pre-competitive research on mini microfilm tubes, so with an internal diameter below 3 millimeters. So you can just have a look on the web page of our current research activities. But let's move to PCM. So which are the most important research activities run at Nano Transfer Lab? So at the very beginning, we started just looking, as I will show, to the application of metal foams, because it was a topic on which I have been working on for more than 10 years so far. But then we decided to follow a new research path. So our main intention is trying to identify new strategies for the optimization of the latent thermal energy storage, okay, which should be cost effective and modular. So we are investigating the application of stochastic and periodic porous structures, trying to identify the most suitable for each application. Then we also look at different high power applications for electronic thermal management, so the application of latent thermal energy storage to cut the peak loads, for instance, and also to adapt the renewable sources and integrate the renewable energy sources to the most important related applications and systems. Of course, one of our PhD students is also working on cold thermal, latent thermal energy storage for refrigerated transport, and also for HVAC integration, especially when the HVAC is connected to solar photovoltaics, for instance. And then, of course, the last one of the last topic that we are studying is the application of hot latent thermal energy storage for heating and hot water, which this topic has been studied for many years so far, but it is still very interesting. So if you want to have a look on our publication, you can just follow these few recent publication on the topic, and I have highlighted in red the ones I'm going to discuss in this webinar. Of course, there are other recent publications related to numerical studies, or experimental studies for water heating, for instance, so hot thermal energy storage, and also on nano PCM, something which is very cutting edge research, what is something that we can say groundbreaking research, looking for something that can really change the scenario. As I told you, I will discuss in particular the publication in red, and the latest one. We can say the latest one. It has been just accepted, and it is now online. Is open source, so you can go and have a look on this publication freely. So let's start with the formulation of the problem, or if you prefer, the problem framing. So we have two different points of view. The first one is the engineering point of view, the industrial point of view, and the other one is the scientific point of view, the point of view of the researchers or scientists, if you want. The first one, the engineering one, so the industrial one, is mainly focused on the application. So we start from the application, then we look at the design rules, and I would say as a mechanical engineer, I'm pretty much involved in this part, even if I'm a scientist. I usually work with companies and industries who are application oriented, and so the development of a product starts from the application. Then we look at the design rules. In this case, we look at the suitable, let's say, PCM. And then we move to the system design by applying the design rules. We are not that much lucky on this because, to my best knowledge, there are not any general rules that can be applied to the design of latent thermal energy storage. So there is a lack. And we are in what is it will follow. We will understand why there is this lack in design rules to be applicable to the system design or latent thermal energy storage design. And then so we start with the system design, and we achieve some prototypes. We produce prototypes, and then we start the optimization process. This is very time and expensive development. So, and if you have a quick look on this, okay, on this path, it is a standalone path, because if we change the application, then we have to start from scratch again. Looking at the scientific point of view, it is a little bit different. Usually, the scientific point of view, or if you want, the scientific path we are envisaging, include the merging of the different problems, because we can identify different problems when we try to propose design rules for latent thermal energy storage. We have a PCM problems, so PCM properties, okay, and then we have PCM, application problems, so the case studies. So what we want to propose here is trying to merge the PCM properties with the PCM-based storage behavior, trying to understand and thus deliver design rules on a system which is based on properties and application. What I mean is that the research path we are trying to propose is meant to define design rules based on the deep analysis and the deep understanding of the PCM plus latent, so phase change process. And from our perspective, this is the only way to achieve reliable design rules in this topic. So the question now are, which is the proper way to redefine the experimental approach to PCMs and thus to latent thermal energy storage? The question is, should we start from the PCM or should we start from the application? Should we start from PCM-based thermal energy storage? So for each PCM, should we start a design path which is meant to identify integrated modular solution? So define a general design approach which will allow to design different thermal energy storage for each different PCM on the basis of a robust procedure. So this is our proposition, okay, for the future. So our research path is meant to define this approach. At Nano Transfer Lab, we are now focusing our attention on low medium temperature phase change materials, so paraffin waxes and sugar alcohols. Of course, we are also interested in esters and in fatty acid. And the idea is to experimentally study cellular structure materials, either stochastic or periodic, for latent thermal energy storage. So tackle the problem using our knowledge on the experimental point of view, and then run a numerical optimization of the 3D periodic structure to maximize the heat transfer in latent thermal energy storage, while at the same time keeping as low as possible the cost. So the modularity is intended here to reduce as much as possible the cost of the latent thermal energy storage, and in this way generate the possibility to deploy cost-effective latent thermal energy storage in many different applications. Okay, this is a slide that I usually discuss all the times because it's very important. What about an ideal PCM for thermal energy storage? If we look at the PCM, Sharma proposed this list of feature properties of which an ideal PCM should exhibit. Of course, it should show a suitable phase transition temperature according to the application. It also should have high latent heat of fusion, of course. And how can we define this? Well, we keep in mind the ice. So the ice is the best phase change material. We can say the best, but of course there are others showing higher latent fusion, latent heat of fusion. However, if we take the ice as a reference, then we can classify and rank different PCM. So the latent heat of fusion of the ice is 335 kilojoule per kilogram. Okay, and so all the others can be ranked. What about the thermal conductivity? It should have high thermal conductivity. Okay, to clear away any doubt, none of the available PCM show shows a thermal conductivity which is high enough. Okay. Usually, the thermal conductivity of the PCM is extremely low. Of course, it should present high density. Okay, with reference of considering, let's say, considering the highs, more than 1,000 is good. Below 1,000 is not that good. Okay. Okay, no subcooling, which means that during solidification, the transition should occur at exactly the phase change temperature. Small volume change during the melting process. Sometimes this property is neglected, but when we start designing something, especially if it is closed, and the volume change can affect the design, mechanical design. It should be chemical stable, non-toxic, non-hazardous, of course, compatible with the building materials, abundant, available, and cost-effective. So these are the let's say, typical properties that a PCM should exhibit. What about the paraffin waxes and why we decided to work with paraffin waxes? Of course, paraffin waxes for low, medium application, temperature applications are very interesting because they show a suitable phase change transition temperature range between 0 to 100, let's say. High latent heat of fusion, 180. Of course, it is half as compared to the ice, but of course, there is nothing as good as water, no? High thermal conductivity, of course, this is one of the major limitation of paraffin waxes. Usually a paraffin is likely to show 0.2 watt per meter Kelvin. And so taking this problem will allow to understand or if you want to start from the worst case, okay, and thus test our procedure. High density of the density of the paraffin waxes the densities are usually below 1,000. Okay, they show also a volume change during melting between 10% and 50%, let's say, but of course they don't show subcooling. They are chemical stable up to 500 degrees C, which is good, high enough. Non-toxic, non-hazardous, and compatible with the building materials, abundant, available, and cost-effective. What about the sugar alcohols? I don't want to spend a lot of time because I won't discuss in detail the sugar alcohols as PCM, but we work for personal appliances, okay, heating appliances, and so we have a little bit of experience on that. They show high latent heat of fusion, the high density, like all the other phase change materials. They show low thermal conductivity, and sometimes they are not chemically stable, so the application must be carefully analyzed, and they show a little bit of subcooling, but not that much. So what about paraffin waxes? Here you have a table. So these are paraffin from the market, RT40, RT45. The thermal conductivity is rather low, 0.2 watt per meter Kelvin. The volume expansion is, in this case, it's 12%, but it can reach up to 50%. All the other properties are quite interesting. So the latent heat of fusion is 165, 170. It can reach for paraffin with a phase change temperature around 70 degrees C. It can reach up to 160 kilojoule per kilogram. So the latent heat of fusion is an interesting property for the paraffin waxes. How can we solve the problem? So the low thermal conductivity, 0.2 watt per meter Kelvin, implies the need of the use of an extended surfaces to allow to allow for the heat to be stored and then rejected or rejected from the thermal energy storage or used, even used. We can say used, okay, stored and then used. The volume change implies that sometimes during the solidification process, voids might appear, and this has to be considered when you have high power applications, because sometimes it might happen that a void is located on a hot surface, on which you don't want a high temperature, for instance. The density, we cannot do nothing related to density, but what we can say is, how can we enhance the performance of the latent thermal energy storage? One possibility that came at first in my mind was the use of aluminum foams, and then I tried to explain why. But then I moved to 3D periodic structure, which is now seen to be very effective. So let me explain why I suggested the use of aluminum foams. So the background is important. I fell in love with aluminum foams in 2006 at the beginning of my PhD students when I was asked to study microgeometries during Air Force convection. So I proposed to my supervisor to build a setup to study the Air Force convection in microgeometries, and I also suggested to study the porous media, so aluminum foams. And from that moment, I struggled against the unmanageable high pressure drop during the active heat transfer. And then when it came to me to a passive application like thermal energy storage, I thought, oh, it's amazing. We can use it here. So I wanted to, at the very beginning, I wanted to start studying the application of aluminum foams as a benchmark, because the aluminum foams, I will show immediately, will let's say, allow for strong, a remarkable enhancement of the performance of the latent thermal energy storage, which cannot be achieved with other enhanced surfaces. So the aluminum foams, or if you want the metal foams, can be considered as a benchmark. Metal foams show intrinsic multifunctional feature, high heat transfer area to volume ratio, good stiffness strength, so we can prepare sandwiches, okay, with aluminum foams inside, or metal foams if you want, and obtain a very strong mechanical part. And of course, the tortuous path enhances the flow mixing capability. This is important in active heat transfer. In the present application, so in the phase change, solid liquid phase change, is not that important. However, the flow mixing capability can be seen as heat transfer capability. Here you have some images taken from the web on different application of metal foam, and of course something also very fancy like MTV Music Television logo. Metal foam is a cellular structured material with open cells, so the fluid can move through the porous structure, and these cells are randomly oriented and homogeneous in size and shape. The foams are usually defined by two characteristics, okay, or identified by two characteristics: the number of pores per linear inch, PPI, and the porosity, so the ratio between the void volume and the total volume. Why metal foams are so interesting? If you look at this table, this is the first study that I'm going to show you as the starting point from our research development on this topic. As you can see here, the metal foams or these cellular structure materials show high porosity, which means, which in this case, if you look, is around 93%. Porosity 0.935 and so on. So 93%, which means that 93% of the total volume is void, so can be filled with PCM. So this is an extremely important characteristic because, as you know, by inserting enhanced surfaces inside our storage, we limit the volume which can be filled by the PCM. So we reduce the capacity of our storage. But when we use a metal foam or a different cellular structure materials, as you will see in the next slide, you just remove the 5 or 7% of the entire volume and on the entire space which can be dedicated or filled with the PCM. But you can enhance the heat transfer by 20 or 30 times. So the initial idea was to study this system in a very simple setup. So we had these samples which were 40 by 40 by 40 millimeters, and we covered those samples with bakelite walls and one glass wall to observe the phase change, and then we inserted that in the Teflon housing, as you can see here, with a window to follow the phase change process. So basically, this is a module. All the surfaces, all the walls were adiabatic. Okay, so we can imagine it as a single element of a bigger system. So let's start with this. Okay, I want to show you just one video as a result of this. This compares the empty box, so without foam, with a 5 pores per inch foam at an imposed heat flux of 20 watts from the bottom. So as you can see, nothing happened at the very beginning for 10 minutes, but after 10 minutes, you see that on the left, the empty box, the melting process started, while on the other side, we just see that the volumes, or the wall, if you want, became a little bit brighter. After 20 minutes, something started also in the system with foam, and the phase change proceeded very fast. In fact, you see here at 30 minutes, which will come immediately now, the phase change in the here we are in the box with the foam reached and overcame the process on the box with the empty without any foam. And after 40 minutes, basically the phase change was completely in the system with foam, while on the other system, only 60%, let's say 60% of the entire PCM was melted. And if you see here, I'm sorry for the low quality of the video, but you see also the convection occurring in the system without foam, which was completely suppressed in the system with the foam. Okay, I don't want to bother you with all the temperature measured inside the samples, but what happened was this. You see here this diagram reported the temperature difference between the junction, so the temperature located inside the plate below of the foam, and the ambient temperature. For the free foams samples and for the empty box. It clearly appears that the performance with the foam is incredibly better as compared to the empty box. So the junction temperature is reduced, which means that the heat flux that was supplied, that was conveyed inside the PCM rather than just in the liquid just melted. In fact, the liquid was extremely hot, extremely superheated, okay? Because the PCM basically is an insulator. It is not an heat transfer medium. So when the melting process started in the PCM without any enhanced surface, what happened is that just a small part of the PCM in contact with the hot surface started melting, to melt, and then proceed very slow up. What happened inside the foam? Here you have a picture. So the heat flux came from the bottom and found a lot of different paths through the PCM, through the box. So this is why at the very beginning it seemed that the heat transfer process was slower as compared to the other one. At the very beginning, the first melted, so the first liquid was observed in the empty box rather than in the PCM, in the foam one. This is why the heat started to go through inside the box, following different research paths through the fibers, and then all the entire box was warmed up before the actual phase change occurred. And surely, as you have seen, the melting process then started from the bottom because the heat flux was supplied from the bottom. So the first part to be heated was the bottom one. But again, the phase change process occurred from inside rather than just from the bottom. And then we have another important result from this. It is basically the fact that the different foams with 5, 10, 40 pores per inch perform exactly the same. So there is not any effect of the pore size. 5, 10, 40 pores per inch PPI foams perform similarly, exactly the same. So a 5.5 millimeter or 2.5 millimeter or 0.6 millimeter average pore size do not have any impact on the performance of the system. So this suggests as something, the research path. So the question becomes, is there an optimal pore size to maximize the heat transfer of PCMs? And then, unfortunately for me, do we really need foams? Okay, let's start from the second question. No, unfortunately, we don't need foam. We can go with a much cheaper system, a much cheaper cellular structure materials. So the idea is now to identify the elementary periodic structure which allows to maximize the heat transfer while minimizing the cost. And this is the research path. So this is the new path. What we did basically is, what we are doing is to use the advanced 3D manufacturing technique to produce a periodic structure, okay, and then run a dedicated test with different PCM to study their heat transfer performance. Develop as a third step that we are developing now and validating a numerical tool to simulate the phase change process in 3D structures. And here I want to stress the point that we are trying to simplify the approach, moving from a 3D, very complex and cumbersome simulation to a 2D simulation, okay? And then run a set of numerical simulation and to optimize the system and using machine learning algorithms. What I mean is we run several 2D simulations or 3D simulation using our cluster here, and we develop and we look for the we develop or build a strong database. And then we run machine learning algorithm to identify the best solution for that PCM, okay? To extract exactly supply exactly the amount of energy, or if you want power, that is needed to be used. Here we are. So we want to pass from a stochastic structure to a periodic structure. And here you have a typical box that we are studying. So here you have our work on 3D periodic structure. So we decided to study pyramidal shape because this shape and the arrangement you see in the picture below can be easily printed. And we decide to keep the porosity at 95% at the very beginning, but it can be easily changed, okay, and study the effect of the pore size. So we studied 10, 20, 40 millimeter of pore size. What does it mean? It means that with foams we studied pore size up to 5.5 millimeter, around 5.5 millimeter, and now we want to move to bigger pores to see if there is a maximum pore size after a maximum pore size. Afterwards, we have a decreasing in the performance of the system because it has to occur this phenomenon, because while increasing, okay, the pore size, we can reach the limit of pore size infinite, which means empty structure. Here you have just a photo of the samples, okay, the empty box, the 40 millimeter from right to left, the 40 millimeter pores, the 20 millimeter pores, and the 10 millimeter pores. Each module was filled with 50 grams of RT55 or RT70 paraffin wax, and then tested during solidification and melting. Here you have the main properties of RT55, okay? And what we wanted to do was to understand the underlying heat transfer mechanism, to be able to develop interesting models, or simple models then, and then validate also the numerical models to study the system. So we used a lot of thermocouples, as you can see here, located at the center, along the center line, or at the corners, here, T5 and T4, inside the system. I don't want to bother you with all this information. Here you have just an image of our blocks, okay, and also the wood housing. One of the major issues in the scientific results available in the open literature is that basically in this system we supply the heat from the bottom using an electrical cartridge, so it's an electrical heating, and then we wanted to translate this information to other applications. It can be done, okay, but it is important is the calibration of the setup. So what we basically want, it has to be very clear that not all the imposed power from the bottom reaches the PCM. Some is lost to the surroundings, okay? And so we perform a calibration very specifically. I don't want to go into details, but to really understand which is the amount of energy that is lost, okay, during the test. So we perform the test by imposing 3 different electrical power, 10, 20, and 30 watts. And the results I'm going to show are relative to 30 watts. Here we have, so here you compare the different. Oh, finally we reach an optimum pore size. So the 10 millimeter pore size revealed to be the best one. And then the performance got worse, okay, passing from 20 and then to 40 millimeters, as compared to the reference one, which is in green here, and it is the reference box. This is the temperature T8 at the center of the system, okay, and the center of the box, and you can see here the heat is imposed from the bottom. This behavior remained the same also in solidification, as you can see here, but and the solidification was run by natural convection, by changing heat in natural convection, and again we obtained the best performance by the 10 millimeter sample. Here you have listed all the time during loading and unloading to show the differences between the systems, but I don't want to go much in details on this table. I can answer to your question afterwards. What happened inside? Which is the effect of the structure. So on the top of this slide you have the empty box. On the right bottom corner you have the best 3D periodic structure, and you see from this image that the temperature inside the empty box is quietly scattered. So there is a great difference between, for instance, T8 in the center and the T3. There can be difference up to 60 degrees C. Differently, in the system with the periodic structure, all the thermocouples are more close one to each other, and the difference is always kept below 20 degrees, almost 20 degrees, something like this. Especially in comparison with the junction one. Just few images on the phase change. It occurred from the bottom and from the lateral walls up to the top. Okay, and this is the just a few images. You can download the videos and have a look on the videos. Okay, but differently inside the PCM. Using the 3D periodic structure, you see it happened immediately from the bottom, from the lateral wall, but the PCM remains on the top. So what's next? What's the next? The next is trying to numerical study this, and we did it. So we started from the box, okay, we meshed it, and then we simulate it. And these are just a few results, if you want. Yeah, these are just few results, if you want. So the phase change process occurs from the bottom up to the top, okay, in the empty box. And this is just a video or animation of the numerical results we obtained, and a fantastic agreement between the temperature measured in the system and as I will show immediately after, and the experimental result was obtained. So here again, for the 3D periodic structure, it happened exactly as we have seen before. So the numerical tool is able to catch the effect of the 3D periodic structure inside the system, and again explain the heat transfer mechanism occurring inside the system. Here we have the numerical validation. So our numerical tool is able to predict the performance of this PCM very accurately. And you see here the comparison between the average temperature of the PCM for the reference, so the empty box, simulated and experimental one. And of course, the same for the PCM with a 10 millimeter size structure. And you see the numerical tool is amazing in simulating the phase change process. So the optimization. So we have the numerical tools validated, and now we are running the different simulation with different geometries, with different pore size, with different porosities, and different also geometries of the system to build the database on which train then the machine learning algorithm. On the basis of the training, the machine learning algorithm will propose one or more optimal solutions. And then we will 3D print those solutions and test if our methodology can be reliable, okay? And what's next? So when we obtain this system, then we can think about the development of modular, cost-effective thermal energy storage. Basically, for each application, we can study the topic from using our methodology, okay, and design the specific 3D periodic structure to be modular, to be cost-effective, to be used to generate the novel latent thermal energy storage. So let me conclude. The experimental approach, in our perspective, needs to be redefined to generalize the result. Porous structures permit to achieve great heat transfer enhancement, but they are not optimized. And so what we propose as a new research path is to integrate the technologies that are available now. So 3D printing, our experimental knowledge, and the machine learning, and so the numerical simulation, and then the machine learning algorithm to generate an integrated approach, okay, which can enable to design very efficient and cost-effective latent thermal energy storage. So the idea is to consider, okay, PCM plus medium. The integration of those two can enable the future deployment of efficient latent thermal energy storage. The question becomes, which is the right heat transfer medium to be used to properly enhance the heat transfer performance of different PCMs? So we have to start from the PCM, because each PCM has its own properties. The developed research path opens a new way, in our idea, okay, to think about the optimization of the latent thermal energy storage as an integrated and modular system. So I want to thank you for the attention on this webinar. I will be happy to answer to all your questions. And let me just show you a new possibility for next September 2020. So with a colleague from Switzerland, Jörg Worlischek and Anastasia Stamatiu, we are organizing the summer school on latent thermal energy storage for a sustainable future, from PCM to final application. It is meant to be held in Vicenza, but we are also open for a fully online streaming of the summer school. So you can go and visit the website of the Latent Thermal Energy Storage School, and please join us. It will be a very interesting summer school. Thank you very much for your attention.
Thank you, Simone, for a very informative seminar. Before we dive into the Q&A session, I would like to remind all attendees will be sent a link with the recording of the webinar. And if you'd like the slides of the presentation, please contact the event inquiries at IMechE, and I'm sure they'll be happy to forward the slides to you. So now we can dive into the questions. The first one is about the feasibility of applying phase change material to cooling of buildings in countries with tropical climate. So the question is if you can, this is feasible, Simone.
Yes. My answer is yes, because we are working with India's colleagues to deploy thermal energy storage for integration to PV, solar power for self-consumption, and to be applied to HVAC systems. So yes, in my opinion, by properly selecting the phase change temperature, so the PCM, phase change material, and coupling the needs, so the heat flux basically that is needed, then it is possible to deploy this technology also in tropical climate.
Great. So the next question is about whether what is cost effective. They're asking what are the target ranges, euros per kilowatt hour, in different applications in your view, for example, for hot water and so on.
So this is a very interesting question, because when we say cost effective, sometimes we might be misled. What happened is that by using a water tank, for instance, this can reach a density, a volumetric density, say of 0.1 cubic meter per kilowatt hours, so 36 megajoule per cubic meter. And by introducing a phase change material, so latent thermal energy storage, this figure might become 0.02 cubic meter per kilowatt hour, so 180 megajoule per cubic meter. This means that our tank or our storage can be 5 times smaller, or with the same volume we can store 5 times the energy. So this has to be calculated in terms of euro per kilowatt hour. So, but for each application, the target can be easily identified on this figure.
Okay. The following question says, how do you think this technology could be used to maximize nuclear energy load to compensate for the times in which wind turbines or solar don't generate enough electricity or don't generate electricity?
So latent thermal energy storage systems have a very let me rephrase. Will be an enabled technologies, in my opinion, for concentrating solar power. So to allow the extension of the power generation after the sun radiation, okay, after the sun set, and this to reply to this question is that of course, in my opinion, latent thermal energy storage will play a huge role in compensate such request of energy. And in particular, if you can imagine, we are wasting tons, I would say tons, even if it is not tons, but tons of megajoule, or tons of energy from in the industrial sector, and these might be also used and stored in latent thermal energy storage to contribute to the power generation.
Okay. Next question is, how does the effect of pore size change with the scale of the latent heat storage device?
This is a very interesting question as well. So thank you. So the pore scale, one has to imagine that this system will be modular. So what will be done in the future is having, I don't know, a tube surrounded by this 3D structure, and then other tube at a certain pitch. And in this way, the scale won't be so important, because each tube will have a reference volume on which deliver the heat or extract the heat. Okay, store on extract the heat, and in this way, I don't see any problem with the scale of latent thermal energy storage device.
Okay, so I think you answered the next two questions, which is, can the method be easily generalized? And could you also consider different geometries with tubes and extended surfaces as well? I think you touched on both sides, but if you want to expand on that.
Yeah, of course. This method can be easily generalized. This is our scope, I would say. This is a pre-competitive research activity, but it has a very strong relationship with the industrial deployment of this technology, and thus, yes, I think so.
Okay, and about the geometries with tubes and extended surfaces?
The tubes and the extended surfaces. So yes, we are now studying tubes and extended surfaces in the lab. So we are performing tests on that, try to understand the generalization of this technique. But the preliminary results are very good.
Excellent. So if there are no any more last minute questions, I'll thank the speaker today. Thank you, Simone, and for a great seminar. And I wish a great rest of the day to all the attendees. Thank you very much.
Have a nice day.